Building highly scalable and reliable code comes with investment into your developer productivity infrastructure. Bloomberg engineers developed tools for running static analysis and performing automated refactoring, which they will share with us today. So at this point, I'd like to welcome T and Marius, engineers at Bloomberg, starting with Marius, who likes repeatable builds and fast computers.
Hi, Helen. Thanks for the intro, and hello, build community. I am Marius, and T is also here. We're from Bloomberg, and today I wanted to share with you an interesting application of the remote execution and workers API that we've been playing with for a year or so. How many of you perform static analysis and automate refactoring across your code bases? If you do, how frequently do you do it, and how much code do you process? At Bloomberg, we do it at scale nowadays using BuildGrid. As I mentioned just now, T and I are both engineers at Bloomberg, and we work on two different teams. I work in the distributed build team, the team that develops solutions for fast, hermetic, and reproducible builds. And we are collaborating with CodeThink on the open source BuildGrid, BuildBox, and Reg ecosystems. T is working on the static analysis and automated refactoring, as also known as STAR team. And the team builds tools and infrastructure for that purpose. They make heavy use of Clang and Haskell in doing so. Just for a little background, our initial use case when we started with BuildGrid, Reg, and BuildBox a bit over 2 years ago was to improve the build speeds, which seems to be the common theme. As an overview, our distributed build farm looks similar to this right now. We use Reg, a compiler wrapper remote execution client, and then we also use BuildGrid for the remote execution and worker API services that provides the execution, operations, cache, bots, action cache services, and we use the PostgreSQL-based scheduler in BuildGrid. On the worker side, we have BuildBox CacheD, which is used as a local cache caching proxy on both hosts, and the BuildBox run user truth worker runtime for the actual execution. BuildBox run user truth is a BuildBox runtime that utilizes the Bloomberg open source project user truth, which allows non-root users to use truth to achieve isolation between builds. This setup gives us cacheable, hermetic, and reproducible builds. A year ago, the static analysis and automated refactoring team started investigating ways to scale the scheduling and execution of their jobs to scan more code than ever. They came up with some ideas on what would be needed to achieve that. And during an internal tech review, the distributed build team realized that what they were trying to achieve was just doable with BuildGrid and friends. That's when we decided to experiment with BuildGrid and see if we could provide more flexibility for this kind of job and avoid having to reinvent the wheel. I will hand it over to T now to introduce us to the static analysis and refactoring jobs.
Hello. Hi, everyone. My name is T from the Bloomberg STAR team. Okay, make sure my audio is good. Okay, I'll get started. I want to get started by first explaining the term STAR. So our full name is Static Analysis and Automated Refactoring. So far, we mainly focused on C and C++, so that in the rest of the presentation, I will use C++ as example language to describe our scenario. Static analysis means capturing certain patterns at compile time. So on the right-hand side, there's an example. We have function foo, which is marked as deprecate, and two other functions using the function foo. So when we compile it with G++ with -wo to enable all warnings, the compiler displays the diagnostic for us saying that the function is deprecate and two places there in the code are using it. Here, declaration of function foo with the deprecate attribute is a pattern. Declaration reference of function foo is another pattern. So that while compiling the code, the compiler is actually doing static analysis for us. Automated refactoring relies on static analysis. After detecting a certain pattern, we could apply a replacement to generate a new source file. By comparing source file using diff, we could generate patches. Other teams could directly apply patches to their code to achieve auto-refactoring. The example on the right-hand side matches the previous one. That is, we know 2 places are using the deprecate function, and we just remove that 2 usages. Assuming we already have the refactoring tool to help us remove that, and now we have the new code. By using git diff, we could have a mailbox format patch, and that patch could be sent to the team or could be used to directly open a GitHub PR. So that achieves auto-refactoring. And this is static analysis and automatic refactoring. Next, I want to talk about how star relative to build process. Actually, they share some similarities. First, they both require involvement of the compiler. For example, we use clang for analyzing C and C++. So clang is a compiler itself, and we basically make use of its front-end API to build AST, and then capture user patterns to do analysis. Also, we have to make sure we are analyzing exactly same piece of software that we are going to build. As a result, we have to apply exactly the same compiler flags to static analysis tool. For example, std-w -d for macros, -i for include directory. Next, they all need to resolve dependencies. Since compiler will be used, we have to provide a whole picture of translation units. We don't want compiler to complain that something is undefined, so we have to collect all the dependencies required by current package. To do that, we have to make use of build because we only know all this information at build time. Luckily, we have compilation database that could be generated at build time by some build systems, for example, CMake or Bazel. The compilation database is a JSON format file which contains commands used for building the project. As you can see, this is an example down there. It contains the directory, the file. So combining these two, we could find out the exact location of the source file needed to be built, and a command which contains all compiler flags we need. The most important one, -i, which indicate the include directory, allowing us to retrieve all dependency headers we need. Differences. Static analysis can be regarded as compiling the code in dry run mode. So there will be no binary file produced, no linking. So that while we collecting dependencies, we don't need binary files. We only need headers and source. This difference is actually important because for resolving dependencies, we don't actually need to install all dependencies everywhere, but just copy the headers and source and archive them into a package, relying on compilation database to record exact paths and make sure we have same toolchain and environment, and then we could reproduce the analysis everywhere. So that makes the analysis not as expensive as build. For everywhere here, let's not consider the architecture and platform temporarily. Here I basically mean same architecture, same platform, but different machines. This is important because of this. We started to consider making static analysis distributed and to wrap the procedure into a pipeline. We could definitely execute it locally, and we still do local analysis sometimes. So next pages, I'll talk about several motivations for why we want to extend it to distributed. First, we say it's very similar to build. So one could imagine that if a package takes very long to build, it could also take very long to analyze. We don't want the analysis to consume local compute resource. So as a result, we want to execute the job remotely. Also, considering that we have thousands of packages building every day, we also want to make the static analysis scalable. So we create scheduler and workers to help us organize and execute jobs. Furthermore, we want the results of the analysis to be reusable. For example, we want to query results of an analysis on a specific package later on. So we have to index package results and store them permanently and provide API for user to query the results. This is the overall view of our star pipeline architecture and the end-to-end workflow. On the left-hand side near the bottom, there's a diagram legend describing a few icons and their meaning. The rectangle one is service. The multi-document one is tool. The cloud-shaped one is for storage, and the black one is database. In our pipeline, we have surveys and storage. We use database to index metadata for package, results, and point to URL in the cloud storage. We build a bunch of Kubernetes surveys to communicate with the database and build grade and provide API for users to trigger analysis and query results. So here, the two major parts are package and analysis. For package, we have ingestion happening at build time or CI time, because only at that time we know how to build the code. And we index the package by using database and then store it on the cloud. For analysis, it could be triggered implicitly by package injection or explicitly by user. After an analysis is triggered, our system will schedule jobs to build grade. And then other surveys will pull the results from build grade asynchronously, index and store it in the same way the package does. There are two pink multi-document icons there referring to tools there. These tools are provided to communicate with build grade. One is to schedule jobs, and the other one is to pull the results. I'll let Marius to talk about more details about the tools. On the right top hand side, there are workers there really execute the jobs invoked by build grade. And since we don't pass package everywhere, we just pass the package URL. So the worker will just receive a URL and fetch the package from the cloud storage on our start pipeline side to do the analysis. This is the overview of our architecture. We have few requirements for the performance and the robustics of the system. I'll describe our expectation, and Marius will talk later on about how the build grade support our demands. First, let's deal with prioritization. So we have job scheduler to organize jobs for us. We want to have flexibility to allow some jobs go first and some to go later. For some, we want the results as soon as possible, while we could wait longer for others. We define the term real time for high priority and non-real time for low priority. For example, if the results of an analysis is used for validating a code commit process, we don't want our analysis to block the process for a long time. So we have to schedule it as real-time job to let it finish quicker. For non-real-time jobs, an example could be generating patches. We could collect a group of interested library and schedule jobs to generate patches, and then we wait till all of them to finish and get them all together, and then send them all to our users at once. We need build grade to support prioritization to provide that flexibility for us. And now build grade already support that, pretty similar to Linux nice values. Next is caching. Let me first give a definition of a job. A job mainly includes several things: a command to run the job, the files involved in the job, including the config files, the command needed, and also files in package, which is static analysis specific, since we run command on the package. We want to resolve a question whether a given job needs to be executed. What I mean by this is we should know if we already have the results for the job. So when we schedule a job to build grade with the commands, the config file, and the package, build grade should provide a caching mechanism to detect if the current job has been executed already and can directly assign result to it, so that no duplicate jobs should be executed, and we could maximize the usage of our compute resource. With the definition of job, we then think about another thing. If we see a job failed, how do we figure out why it failed? The goal here is to have a way to let us reproduce the remote execute job locally to debug it. In order to achieve that, we need to know all the details of a remote job. Before achieving that, we should first have a unique representation of a job, a unique ID. So every time when we schedule a job, we should get the unique ID. By using that unique ID, we can then query build grade to give us all the details about the job, including commands it used, config files, the package, same as the job definition, and also the results, including the exit code, the output files, std out, std arrow. So with all this, we can then run it locally to get the output, compare the results, and debug it ourselves. Here is an example of the interface we have so far. It is called BGD browser. We are able to browse the action of the jobs, see the command the job run, and std out, std arrow. Also, we have the input directory and output results, and we could download them if we need. So all these could make our debugging easier. This is the end of my part about our star pipeline. I will then pass control back to Marius so that he could share more details about how Buildgrid support our star pipeline. Thanks.
Hi again. So obviously the main feature that we're looking for here was scheduling of jobs on remote workers. And luckily, the Remote Execution API provided quite a few bells and whistles to make that a great option. Some of the API features weren't implemented early on since they weren't necessary for compilations, but a good subset has now been implemented in Buildgrid and Buildbox worlds, which makes Buildgrid even more flexible for arbitrary remote execution. Now, the nature of some static analysis jobs makes them require potentially long amounts of time to finish. Unlike builds, though, where one needs to wait for individual object files to link, the caller here doesn't need to wait for all the jobs to finish to handle them. That's why we implemented support for async job submission using the execute instead of the wait execution request the Remote Execution API offers in RExec. As a reminder, the wait execution method returns the operation, which can be later used to look up the status and fetch results. We will be opening a PR upstream for this feature as well. So what we do now is, number one, we use RExec to submit async jobs using the execute request. And then we take note of the returned operation, and we keep polling for the operation status using the gRPC CLI. Once the operation completes, we use cast download, a simple cast downloader in Buildbox Common to download the results. Now, since we were expecting very high volumes of jobs going through asynchronously, we needed a way to easily find jobs of interest. The operations proto does allow for arbitrary string filter, which we made use of here. We implemented an extensive operations filtering language in Buildgrid, which can be used by gRPC CLI and other clients to narrow down the search domain. For example, this filter on this slide queries for operations completed after that timestamp and orders by completion time. Other supported parameters include operation name, queue time, start time, tool names, versions, invocation ID, etc. You can see more details about this language in the Buildgrid documentation. Now, Buildgrid browser also supports this filtering language, and this is the same screenshot that T shared earlier. And the filter here that was used was pretty much just looking at the completed operations and sorting them by time in sending order, which makes it easy to find the recently finished jobs here. Buildgrid initially had a single type of scheduler, the in-memory scheduler. And with this volume of jobs, that's not ideal. We built a new Buildgrid scheduler, which is more horizontally scalable now. And it is a PostgreSQL-backed scheduler and makes Buildgrid easier to scale by removing the single point of failure there. It's very similar to the in-memory scheduler, but instead of keeping state in memory, it keeps state in PostgreSQL. We do try to take advantage of gRPC connection stickiness where possible and try to minimize the SQL queries where possible as well. Now, since we only needed the results for a few days in this case, we also implemented some maintenance features for job lists and operations from the PostgreSQL database, which ensure the size remains reasonably low and performs well. To put all this into a picture, let's look at this diagram. RExec is used to asynchronously submit the jobs, and that also includes uploading the inputs. This is a better choice here for arbitrary commands compared to rec, which is just a compiler wrapper. When a job is submitted, Buildgrid returns the operation to RExec, which is taken note of on that end. Now, as opposed to our build firm, here we use Buildbox run host tools workers. And Buildbox run host tools here runs in custom Docker images containing the static analysis and refactoring tools running on Kubernetes instead of the VMs that the build firm uses. The bots handle the execution of jobs here. On the other end, gRPC CLI is used to periodically look up whether the relevant operations were completed. And when that happens, cast download, a simple cast downloader tool from the Buildbox common repo, uses the action digest that was received to download the results. We still have BuildGrid set up with the PostgreSQL scheduler and its cleanup mechanism. As T mentioned earlier, if, say, PR invokes static analysis of already analyzed code, the results can be reused as well, saving both time and compute here. Now, I know we've been saying that we need to run these jobs at scale, but scale is pretty subjective. To give you a better idea, let's take a look at some summarized metrics. On a weekly basis, we have around 1 million static analysis and refactoring jobs going through BuildGrid now, and the workers process 14 million files in about 600 compute hours a week. Just for a comparison, a week has 168 hours, so that's quite a few jobs there. So what's next, you may ask? Is this project done? We have a pretty good platform for remote execution now, and we handle a few million jobs a month. However, there are always areas of improvement, either things that were omitted in the beginning or things that will allow for better scalability. You may have wondered, how does the PostgreSQL scheduler perform with BuildGrid? Well, it's a SQL database, so all strong data guarantees come at a cost there. And well, BuildGrid is reasonably responsive with the current volume of jobs, and with all the cleanup functionality we've implemented to keep the database size relatively low and ensure better performance, we know it will become an issue one day. To ensure that BuildGrid can handle an ever-growing number of jobs, we are creating a new scheduler type in BuildGrid from ground up, and we will be using RabbitMQ instead of PostgreSQL, and that will be in the critical path instead of the SQL. The design around the RabbitMQ is quite different than the simpler versions we've had so far with the in-memory and PostgreSQL back schedulers, in that the data model here is a queue. We've been discussing this design in the BuildGrid mailing list since last year, and the overview of how it will all work can be found in the BuildGrid documentation. This is in progress, and if you're curious, you can look at the docs and see how it will work. Regarding the bots, Buildbox Worker is flexible in the sense that it allows you to plug in any runtime you wish. I had mentioned the Buildbox Run user truth and the Buildbox Run host tools runtimes earlier on. But we will be going a step further and implementing a Buildbox Run OCI runtime, which will make containerized bots a first-class citizen for Buildbox, making it very easy to use containers for remote execution without having to deal with the complicated setup of Kubernetes. That's all we had for today, and we hope you enjoyed hearing about this use case. I think let's open the floor to any questions you may have.
All right. Thanks for this talk, and definitely really interesting to hear that you're planning to invest more in the containerized bots as well. Let's open the floor for questions. While we wait, if there's anything else you'd like to share specifically related to that last point, that'd be great as well.
I think we shared everything so far. There are some links here for anyone interested in using those projects or contributing or just giving us any feedback.
And the scale at which you run, what size team do you have that supports that type of developer tooling infrastructure for that scale?
I would say that's a bit of a complicated question because there's various teams working around this. I think that the distributed build part is about 10 people, and the star side is around that size, I believe, too. Is that right, T?
It's also around 10 people there. So we maintain the static analysis tool and the infrastructure to cooperate with the distributed build team. Yep.
Yeah, it's sizable investment, which is great. Yeah.
We want high quality.
What are some unexpected challenges that you faced while building the system?
I would say that from the remote execution side of things, we did have to ensure that uploads and things like that work well for this kind of job. And that is why I went with RExec here, so that we have a better control of what to upload compared to rec, which uploads just the compiler dependencies. That's one of the early ones I can think of. Not sure I have anything too specific. The scheduler, we are trying to make it more scalable because it will become a problem. We initially did start with the in-memory that we had at the time, and it was great, but we wanted to have multiple build grid hosts in a cluster, so we couldn't really do it that way.
All right. And also, do you use other tools like Coverity or SonarQube?
I don't think so, at least not on this side of things.
All right. Well, thank you for your time again.